Explaining complex power, apparent power, reactive versus active power, instantaneous power, and also concept of power factor PF and reactive factor RF. Consider this one-port simple network with equivalent impedance Z shown for this port, and the voltage across the port V hat indicating phasor voltage, and the phasor current is I. We are talking about sinusoidal steady state power analysis. So it means, let's say the voltage across this equivalent impedance is V, amplitude Vm or magnitude Vm cosine omega t plus theta V. That's the general form of a sinusoidal steady state voltage across this load. This is in volt, and omega is just radian per second in the form of 2 pi f, or which f is frequency hertz, or 2 pi over t. T is the period of sinusoid in seconds. Theta v is the phase in radian. So this is the voltage, and let's say the current I is in the form of Im cosine omega t plus theta I. Same argument. Instead, just this is in amp, Im is the amplitude in amp, and omega same omega, and then theta I is the phase of current in radian. We know that this can be also represented in phasor format as V phasor is Vm, just phase of theta V basically is in the form of effectively representation of Vm e to the j theta V. And then for phasor current, we have I phasor, Im, phase of theta I, which is effectively representing Im e to the j theta I. Okay, so instantaneous power P instantaneous obviously is just, by definition of power, it's just in the form of just V times I, which is, when we follow this, is Vm Im cosine omega t plus theta V times cosine omega t plus theta I. Using trigonometric expansion, we have Vm Im over 2, and then we get cosine theta V minus theta I, and then we get cosine 2 times omega t plus theta V plus theta I. Okay, and then this is, of course, we're talking about instantaneous power is in terms of watts. Okay. So we are also very much interested in finding the average active power. So P average, which is the average active power, which basically represent the average power that is dissipated in the resistive portion of this equivalent impedance in the form of thermal dissipation, is just the integration over one period of time of this cosine 0 to t P instantaneous dt. Just what we are computing here is just the average of instantaneous power across one period, over one period of the cosine in this sinusoidal steady state analysis. So we have 1 over t, let's factor out Vm Im over 2 across this, leaving integral from 0 to t cosine theta V minus theta I dt, that's the first component here, plus integral 0 to t cosine 2 omega t plus theta V plus theta I dt. Okay, great. Now we know omega is just 2 pi over t, so this component here is 4 pi over t times t. Okay, we know that the integral over one period of the original cosine from 0 to t of this whole thing is 0. So this goes away, and therefore the average active power becomes 1 over t Vm Im over 2, and then this is a constant, so we take it out of integral, so it's cosine theta V minus theta I. We end up with just integral 0 to t dt, and this thing is just t so it cancels out with denominator. So that's why the average active power becomes Vm Im divided by 2 cosine theta v minus theta I. Okay, so this is average active power, or as I said, dissipated power across this load. Okay, and by the way, we know that VRMS, or RMS voltage, is just Vmax, or peak of the voltage, divided by 2, and we know that IRMS is just Imax divided by 2, so square root of 2. So effectively, Vm Im divided by 2 is just VRMS times IRMS. So that's why this can be also written as VRMS times IRMS cosine theta v minus theta I watts. Okay, so this is what is referred to as total average active power. This is referred to as apparent power. So this thing is apparent power. In order to get the average active power from apparent power, we need to multiply it by this cosine theta v minus theta I term, which is referred to as power factor, or active power factor, which is PF. Okay. And by the way, apparent power of course has a dimension of watt. Okay. Now think of this from the perspective of the initial phasors that we presented here. So it's as if we are saying that the average active power is 1 over 2 real part of V phasor I conjugate. Because if you compute this, you can easily see we are talking about 1 over 2 real part of V phasor is Vm e to the j theta v, and then I conjugate is Im e to the minus j theta I. So Im e to the minus j theta I. So this is 1 over 2 real part of Vm Im e to the j theta v minus theta I. Okay, and obviously the real part of this is exactly what we got here. So because the e to the j theta v minus theta I is cosine theta v minus theta I plus j sine theta v minus theta I, real part just takes the real part out of it, and we get this guy. So this is the way we also compute active power from the phasor equivalent of voltage and current across a load. Now, with this definition, we can actually generalize this. So this gives us a hint that, hey, maybe we can define a complex power. So complex power is just 1 over 2 V phasor I phasor conjugate. So this is the complex power. The dimension for this is not anymore watts. It is just volt amp. And the average, so this is average by the way, and the average active power is just real part of the complex power S. So at the same time, one can wonder that, okay, what about the imaginary part of S? Well, we can define something that is referred to as Q, or reactive power. So Q, reactive power, or imaginary power, as imaginary part of S, which is basically Vm Im divided by 2 sine of theta v minus theta I instead of cosine. So this is still apparent power, as we saw before, okay, in watts, but this is reactive factor, or RF, reactive factor. And the overall outcome is not in watts, because this is not a real power. This is an imaginary power. And the value of this is referred to as volt-amp reactive. So the dimension of this imaginary power is what is referred to as volt-amp reactive, or VAR. And this is actually a representation of the energy stored in inductor or capacitor in a circuit on average. And depending on whether that energy is being absorbed by the component or is generated out of the component, it is referred to as absorbing VAR or generating VAR, and sometimes it is said to be magnetizing VAR. So don't be confused if you hear these words like absorbing, magnetizing, volt-amp reactive, or you hear generating, magnetizing, volt-amp reactive. Okay, I hope that you find this summary helpful in terms of clarifying what is the difference between complex power, apparent power, reactive versus active power. Reactive power, also referred to as imaginary power, or the power of the energy stored, and instantaneous power, and also concept of power factor and reactive factor. Just one last note that regarding power factor, if you take a look at what we got here, and if you rewrite this, that for this specific one-port element or component we showed here, the phasor relationship between the voltage and current is like this, and Z is the equivalent impedance. So if I rewrite this in the form of Vm e to the j theta v is equal to Z Im e to the j theta I, you can see that Z effectively is Vm over Im e to the j theta v minus theta I. So we can see that obviously magnitude or amplitude of Z, magnitude of Z is Vm over Im, and we can say phase of Z is just theta v minus theta I. So no wonder sometimes this average active power is also referred to as V RMS I RMS times cosine phase of load. And in real life, in real implementations, when power generators are sending electrical energy to, or electrical power to houses and consumers, usually most of industrial loads or consumer loads are in the form of capacitive load, inductive load, because of turns, and because of that inductive load, effective inductive load, then Z has a positive imaginary part, and therefore you can see that in that scenario cosine, it's a positive phase, and that's why we are seeing it's a lagging power factor scenario, because current is lagging voltage, because of, again, the fact that equivalent load of the system is mostly inductive. So again, the expression like leading power factor or lagging power factor is just indicative that whether voltage is ahead of current, or current voltage phasor is ahead of current phasor, or voltage phasor is lagging the current phasor. I hope that you find this helpful.